Okay, we should be recording. Hey, folks, welcome to the February. Now it starts recording. Okay, hi, folks. Welcome to the February Northwest C++ Users Group meeting. A couple of quick announcements before as we start. First is we now have a meetup group. So in the next month or so, you'll see that starting to come live. We'll get links out on the email and the website. So I'd like to thank JFrog and Conan for sponsoring that meetup for us this year. So everybody give them a big round of applause. Associated with that, now that we have an official meetup group, that actually opens the door for us to get back in and start using the Microsoft Reactor room. That has opened up. So we're going in April, we are going to try our first in-person hybrid meeting as well. So keep an eye out for that. You'll be able to attend in person at the Microsoft Reactor room, or we'll keep the online meetings going as well. As far as pizza, we'll kind of bring that up as we see what people are doing and where things are playing. So probably don't worry too much about pizza right off the bat, but we're looking to bring that back too. So we're coming back to live. Let's see. I think we had Chris, Brett, any conference stuff you guys want to touch on before we go?
I think Chris can probably talk more about the C++ Now and C++ North.
Yeah,
CPPCon is still ways off, so in planning.
Yeah.
So
the C++ Now submission window is in theory closing the moment Sean submits. And technically, it's been closed a week, but we have a backdoor for Sean. CPP North submission window is open now. The CPP Con submission window will open in May.
Okay, thanks. And with that,
the only thing I want to say is that if you want to volunteer for CPPCon, just put it on your calendar for October 1st through the 6th, or September 31st through the 36th. So.
And as usual, Brent, sign me up.
Okay. Sounds good.
Okay, with that, I will hand it off to Sean Parent, who basically needs no introduction, speaking on what's your function. All yours, Sean, and thanks.
Hey, thank you. So a little bit about this talk. I'm actually going to use you, the audience, in this talk. My teams started putting together a course to be taught inside at Adobe, and we've derailed our own effort multiple times at this point, but we plan on launching next month. And so I'm going to be vetting some of the material from the course. And I'm not starting at the beginning, which made this talk a little difficult. So as I was kind of walking through it, at one point I had to slice in some information further down. And because it's a very long course and we only have an hour, I tried to figure out kind of a snippet at the beginning that works fairly well. So this is going to be kind of a an incomplete snippet out of the middle of some material. But if you guys want to leave in chat or send me an email, my work email is sparent@adobe.com. With any comments about this, I would appreciate it. The course we're putting together is based off my Better Code series of talks, so you can kind of look those up online. And we're trying to build a thread across all of the material to carry it through. And we've been shuffling the order of things a bit. So this is a slice from the algorithm section of the talk. And this is going to come after we cover contracts. So we're going to actually open the course with a discussion of contracts and how to specify software. And I realized as I went in, I was going to have to replicate some of the material. And so you'll see it's kind of dropped in a little randomly to discuss contracts and code correctness. So that gives you some setup here. Now, I think functions are often ignored. As we're writing software, we tend to have a lot of discussion about how to write types and type hierarchies and object networks and designs, and we do pay some attention to some of the more serious algorithms, but functions is just kind of a basic useful abstraction for constructing software. It's ubiquitous, but we still tend to ignore them and not focus so much on them. So I wanted to explore a little bit about functions and how you go about writing a good one and identifying them in your code. So if we take a line of code, just a very simple line like this, I could ask you, what does this line of code do? And I'll pause for a moment. You should be able to figure it out. It's not intended to be tricky, but it probably took you a moment to figure out what it does and make sure you were correct. Right? Now I could assist your understanding by sticking a comment on here and saying R is the minimum of A and B. Right? So that helps. But it helps a lot more if I just use a function. So if I wrote this, you'd have no trouble seeing exactly what's happening right away. So naming an operation, even a simple operation, lowers our cognitive overhead. Right? Now, when we write a function, we want to specify it, pulling in a little bit from our contract section. So this might be an implementation of the min function that we were using. Now you notice the comment there gives us the semantics. And so what we're doing is a function allows us to associate a name with a set of semantics. That simplifies how we understand our code. So once we have the specification of the function and the name of the function, we don't have to care about the implementation anymore. For the most part, we can just use it. So functions allow us to build a vocabulary and focus on what the code does. So how do you go about naming a function? Well, here's some guidelines. Operations with the same semantics, the same meaning, should have the same name. So where possible, follow existing conventions. Names should describe the post conditions, right? And they should make it clear where you're using the function, what the function means. For properties and constant-ish, I'm using ish there to be any, log n or polylog n, anything that's better than linear time. So for properties and constant-ish complexity, use nouns for names like capacity, use an adjective like empty. Empty itself is a little ambiguous as an adjective. It could be another part of speech, but it's used by convention. And so by the first rule, it's a good name. And copular constructions, which are things like, is blue. For higher complexity operations, use verbs if possible. So things like partition. If we had a functional version of sort, I've seen some libraries call it something like sorted, which is an adjective and doesn't convey that this thing's doing work. So using a verb is better. So if we said, A is equal to a sort of B, that's better than not A is equal, or don't use A is equal to sorted B. For setting properties, prefix the verb with set. So i.e. set capacity. I borrow that guideline from Objective-C. It's not something you see a lot in C++, certainly not in the standard library. But I find it avoids confusion over pairs of calls. Like in the standard library, we have size and resize and capacity and reserve. And those pairs get confused a lot, which one goes with which. So if you had size and capacity and set capacity, it would be much more clear. Okay. But for those specific examples, go ahead and use the standard names. Don't try to invent your own vocabulary for those. So clarity is of the highest priority. So don't construct unnatural verb phrases, which means sometimes you're going to violate the rule. So use intersection of A, B, even if the complexity of that is not constantish, as opposed to creating some unnatural verb phrase like calculate intersection. And don't use verbs like get, right? They don't add anything. So just use name and not get name. So specifying a function. Well, at a minimum, the specification should be a sentence fragment defining the postconditions of the function. State any preconditions that are not clear from the types in the function signature for the function arguments, and clear by convention. And we'll cover some of those conventions in a minute. So this would be a fairly decent specification for a function, right? Squirty, right, returns the truncated square root of x. X must be greater than or equal to 0. Argument types. The terminology here, as far as let, in, out, and sync arguments, I'm borrowing from the val language, which I didn't mention. That's another project from my team at Adobe right now that Dave Abrahams brought with him. It's a Swift-like language that pushes the idea of mutable value semantics basically as far as you can take it. It's a research language we're exploring. And one of the things we're doing internally is starting to look at using val as a teaching tool. We find a lot of things that we'd like to express in C++ are just cumbersome, and it's much more clear to express it in val and then say this is how that maps onto C++. So that's where the terminology here comes in. So if we have, for our argument types, let arguments, these are constant arguments, in arguments. These would be represented by const L value references or by value for known small types and invocable types. And the invocable types is just a strong convention in C++ from the standard library, and it's there because oftentimes invocable types are actually effectively have no size. They would be a size of 1 because they're an empty class that you can just call. In-out arguments pass by L value reference, but prefer sync arguments and a result to an in-out argument. So a sync argument passes by R value reference or by value if it's a known small type. And I also use pass by value when it's a template dependent type to avoid forward referencing, since they have the same signature, and it's just a pain to constrain a forward reference to only be a sync argument when that's what you want. What's not on this list is set arguments, which are out arguments, and the reason for that is they're almost never needed. So prefer using function results to out arguments. So spans, views, iterator pairs, and so on are a way to pass a range of objects, some sequence of objects, as if they were a simple argument. So the value type of the range, if it's in, or if it's a let variable, that should say let, being const, would be an input range, not const for in out, and an input iterator pair if it's a sync argument, which I had just added a minute ago to my slides, but it didn't show up in my build. So now in C++, we have a set of implicit preconditions on functions, which frequently are not stated and just assumed. One of those is object lifetime. It's to say that a caller must ensure that referenced arguments are valid for the duration of the call. We also have validity, which is an invalid object cannot be used as an argument. Right? So you can't pass an uninitialized int to a function. Typically doing that's just going to trigger undefined behavior when that int gets referenced. There's also something that is a little more hidden in C++. So here's a piece of C++ 20 code where we've got a vector A with the values that are shown there. And we're going to erase all the instances of the first value of the vector. So all the zeros. So do people see the problem with this code? What do you expect is in A afterwards? I know everybody's muted, but if somebody wants to just jump in and yell it out, feel free. Here's what that would output. Okay, so you can try it on Godbolt if you want. So you would think it would be erasing all the zeros. It erases the first two zeros, and then it erases all the ones. Does anybody see why? What's going on here is this fails because a sub 0 is passed by a reference, and it's aliasing the vector. Okay, the standard is really inconsistent in how it deals with aliasing and mutations. Unless aliasing is explicitly allowed in the specification for a function, avoid it. Right. So what's going on here is we start removing the zeros, and what we're going to do is we're going to skip over the first two zeros and move down that first one. And once we've moved down that first one, now a sub 0 contains 1. Now we're going to go past that, and a0 will continue to be 1, and we're going to remove the remaining 1s and not the remaining zeros. So it's surprising behavior. So if you wanted to express that correctly, you would have to break the aliasing. So one way to do that would be to make a copy of a sub 0 and pass in the copy. So the law of exclusivity is borrowed from Swift, and the term was coined by John McCall. The idea is to modify a variable, exclusive access to that variable is required. C++ doesn't enforce this rule. It has to be manually enforced. But if you violate this rule, a lot of things tend to break. So the law of exclusivity has far greater implications outside the scope of this talk and outside the scope of just function arguments. So you might be interested in learning a little more about the val language, which kind of takes the law of exclusivity to the extreme. Now ranges. When we're dealing with ranges by convention, an iterator pair denotes a valid half-open interval. Okay. So I can have the function transmogrify here that takes two forward iterators, and I'm going to say that this is going to transmogrify the elements in the range F to L. And I don't have to specify in my specification that the L is reachable from F, and everything, all the iterators between F and L are dereferenceable. That's implied by just the fact that I'm passing a pair of iterators. It's a strong convention. We also have implicit postconditions in the language. So validity of references. So any references such as pointers, iterators, to an object is assumed to be invalidated if the object is mutated. So if you're modifying a container and you have an iterator into that container or a reference to some object into that container, then that reference or those iterators are invalidated unless the standard specifically says otherwise. Right? And the same should be true for user-defined code. A returned reference must be a reference to one of the arguments to the function or a part of one of the arguments, and is valid until the argument is modified, which would invalidate it, or its lifetime ends. Right. So when I look at vector back, that's an example of a function that's returning a reference, which is into a part of the vector, which is an implicit argument to the member function call. So that reference to the back element, I can assume that it's valid until my vector is modified or the lifetime of the vector ends. Okay. If I want stronger guarantees than that, I need to state them. Sequences. So let's talk a little bit about how we represent sequences. First, for a sequence of n elements, there are n+1 positions. And so how do we want to represent a range of elements? Right. Well, there's problems with using a closed interval. Right. Do people see what it is? If I'm trying to represent sequences with closed intervals, I have no way with a closed interval to represent an empty interval. With open intervals, I require one additional position. So I require n+2 positions. So half open intervals have a significant advantage. And by strong conventions, we're half open on the right. So reverse iterators kind of flip that. There's always the equivalent going the other direction. Okay. So PP represents an empty range at position P. But all empty ranges are not equal, which sometimes confuses people, because an empty range still denotes a position itself at position P. So we can think of the positions as the lines between elements. So a lot of people, when they're trying to reason about iterators, this is kind of their view of it, right? I've got a range from first to last, so I've got a pointer to first and a pointer one past last. Okay. So that's kind of a difficult mental model to deal with, and it's a little asymmetric. If instead we think about it as the positions being between the elements, it's simpler to reason about. It makes more sense, and it's very clear then what an empty range looks like. Now, there are limitations with half-open intervals. The last element cannot be enclosed if the position type is the same as the element type. So, for example, you can't express the range int min to int max using just integers. Right? Now, there are different common ways to represent half-open intervals. A position F is a sequence. In a sequence can be denoted with an index, pointer, or iterator. The only requirement is that F be incrementable to obtain the next element in the sequence. Right, so I can have a range first to last. I can have a range that's takes a position and a count. Okay, those are typically suffixed with _n, like copy n. I can have a range that takes a first position and a predicate, so it's got a test to determine the delimiter. That would be an until function. I can have a sentinel, like a null terminated byte string at the end. This is very similar to having a predicate, but it's a specified value. Right. I can also have an unbounded range, which is dependent on something else. So you see that in algorithms like copy, where you have a first, last, and then just an output iterator. In fact, most of the times you have just an output iterator. It's unbounded, right? Which means the requirement on the length of that range is dependent upon something else. In this case, copy. It's the source for the copy. For a given variable a in both C and C++, it's guaranteed that the address of a +1 yields a valid but not dereferenceable pointer, right? So for any variable a, at a to at a +1 is a valid range, right? This is sometimes useful if you have a range algorithm and you want to apply it for just one element. Now, there's a very good web page here on CPP reference. I find a lot of people don't know about this. This is not a link to the web page for the algorithm header. This is a collection of the algorithms in the standard library on one page. So this includes the numeric algorithms and the range algorithms in a handful of miscellaneous algorithms. So it's just kind of a nice summary if you want to see the collection of everything that's in the standard library. Now let's talk a little bit about generic algorithms. If I have a function find defined like this, find FLA returns the position of the first element in the range FL that is equal to A. Then I can find a given element like so. But how do we know that find will find a value? Well, within the standard, iterators must meet the requirements of legacy input iterator, which is how std_find is defined, which means that FL must form a valid range, which we would just implicitly assume. And the value type must be a quality comparable to the iterator value type. So we need to understand a little bit about what those requirements mean. So I think it's important that we understand a little bit about requirements and guarantees. A generic algorithm is specified in terms of a set of requirements on its arguments. The requirements are a set of concepts and preconditions, which, if satisfied, guarantee the algorithm's performs as specified. The C++ standard contains tables of named requirements and concepts. Concepts and preconditions are closely related, and both ideas are rooted in Hoare logic. A given type or operation guarantees it satisfies some requirements. Guarantees are provided by modeling concepts and ensuring post-conditions and class invariants. The description of each type in the standard will specify it is a model of a concept, as well as specifying the semantics, the post-conditions, class invariants of operations and objects. So by matching requirements and guarantees, we create software which we know works. Now, concepts. The term concept first appeared in the paper Fundamentals of Generic Programming by Dennert and Stepanoff. It was defined as this. We call the set of axioms satisfied by a data type and a set of operations on it a concept. In C++ 20, we have a language feature concepts, which is a set of syntactic requirements with a set of specified in documentation semantic and complexity requirements. Right? So the meaning of the concepts in the standard is not just the matching syntax, it's the semantic requirements around that matching syntax. So as with spoken language, we're associating meanings with words. Now in code, I still find even this idea is controversial. This is a quote which I've used in many of my talks. This was from a conversation in email that I was having with Craig Silverstein now over a decade ago when I worked at Google about having strict semantic requirements. And this was Craig's response. Names should not be associated with semantics because everybody has their own hidden assumptions about what semantics are and they clash, causing comprehension problems without knowing why. This is why it's valuable to write code to reflect what code is actually doing rather than what code, quote, means. It's hard to have conceptual classes about what code actually does. Unfortunately, sometimes I see similar attitudes to this kind of bleeding into the C++ standard itself, which we'll see in a bit. So legacy input iterators and the quality comparable are concepts, right? The reason why they're legacy is they predate the C++ 20 concepts, which have similar ideas, but we haven't redefined yet the entire standard algorithm, such as std-find. But the ideas contained within them are closely associated. So concept semantics usually are specified in terms of existential and universal quantifiers. So things like for all and there exists. However, there's also an implied precondition that the argument is within the domain of the operation. Right, we'll talk more about domains of operations in a moment. So we say that a concept is modeled by specific types or that the type models the concept if the requirements are satisfied for these types. By stating that a type models a concept, a type is providing a guarantee that it may be used where a concept is required. Now, contracts, I'm going to cruise over very briefly here, just because it's important to understand a little bit about preconditions. So contracts, or design by contract, is a systematic approach to ensure that values passed to and returned by an operation satisfy specific assertions. Right. This is the definition for design by contract that Bertrand Meyer gave initially. If the execution of a certain task relies on a routine call to handle one of its subtasks, it is necessary to specify the relationship between the client, the caller, and the supplier, the called routine, as precisely as possible. The mechanism for expressing such conditions are called assertions. Some assertions, called preconditions and postconditions, apply to individual routines. Others, the class invariants, constrain all the routines of a given class. A precondition is a condition that must be satisfied by the argument values to a function or by the state of the system, a global precondition for the operation to execute correctly. Correct execution can include returning an error. So FL must form a valid range as a precondition. Not all preconditions can be asserted in code. So, for example, it's very difficult to assert FL is a valid range in code. So, for example, I have the precondition, for a function f, which is taking a pointer to an integer p, that I have the precondition that p is dereferenceable. There's no way for me to assert that precondition in code, because if I dereferenced a non-dereferenceable pointer, it would be undefined behavior. So we must still validate and prove our code by hand. Most concepts cannot be asserted in code because of the existential and universal quantifiers, and many preconditions cannot be asserted in code. So, a little bit of an aside here. Security is something that gets associated with correctness frequently and with safety, which is a whole topic that I'm not going into in this talk. But a secure interface is an interface where all preconditions can be and are validated, which can be stated another way, which is to say that the interface for a secure function must have no preconditions. And a secure system requires the interface is secure and all the code within the system is correct. So that doesn't mean that if you have all correct code that you have a secure system, but that is a requirement. So if your organization is concerned about security, you should be concerned about correctness and not just safety. So postconditions. A postcondition is a guarantee about the result of an operation. So the result in this context is used broadly to include modifying arguments and any side effects. So for example, the result of find FLV is an iterator within the range FL. So that's a postcondition of find. Class invariant is a postcondition that applies to all operations, including construction on a class. So this brings us to talking about domains and partial functions and how they relate to concepts. So the old SGI-STL less than comparable concept was defined like this. This is the work of Alex Stepanoff. The name of the concept was less. The expression is x less than y, must be a valid expression. The preconditions are x and y are in the domain of less than. Okay. Those were the requirements. Now compare that to the C++17 concept, CPP less than comparable requirement. We have the expression A is less than B, it's convertible to a bool, and less is a strict weak ordering relation. What's missing? What's missing is the requirement of the domain. Domain of an operation is defined in the C++ standard, but surprisingly now it's only in the context of iterators. This passage is used to refer to the domain of operations, but that has been narrowed to the domain of equal for iterators. So this is how the current C++ standard, this is the only place where they define domain of operation now. The term the domain of equal is used in the ordinary mathematical sense to denote the set of values over which equal is required to be defined. This set can change over time. Each algorithm places additional requirements on the domain of equal for the iterator values it uses. These requirements can be inferred from the uses that algorithms make of equal and not equal. So if we have the expression A not equal to B, it's context convertible to bool. Operational semantics is A is not equal to B, and we have a precondition that AB is in the domain of equal equal. What was part of the definition of concepts in Alex Stepanov's work in general has been weakened to a requirement on a single operation on iterators. So I've proposed a fix for this, or at least a partial fix, in a standard proposal P2345, a wonderful number for a standard proposal. I just got lucky. I didn't request the number. And that's that we reintroduce the name, the term domain of an operation. It says the term, and this is my proposed wording, the term domain of the operation is used in the ordinary mathematical sense to denote the set of values over which an operation is required to be defined. The set can change over time. Each component may place additional requirements on the domain of an operation. These requirements can be inferred from the uses that a component makes of the operation and is generally constrained to those values accessible through the operation's arguments. So a partial function is a function whose domain is a subset of the values for the type of the operands, which means that the operands themselves have some precondition. So because machines are physical and finite, many operations are partial, right? Addition on signed integers, for example, is a partial operation. Overflowing on addition yields undefined behavior. Division is a partial operation. You can't divide by 0. And so forth. So we need to learn to manage partial functions with care and ensure that values are within the function domain. This gives us some axes of freedom. Guarantees can be strengthened without breaking existing code. So for example, stood basic string only guarantees that the value of a move from string is valid. It doesn't guarantee what that value is. But in a future standard, we could guarantee that the value is empty without breaking any existing code, right? Because empty is valid. Requirements can be weakened without breaking existing code. So for example, stood merge currently requires a strict weak ordering. In the future, that could be relaxed to a partial ordering without breaking any existing code. Weakening a guarantee or strengthening a requirement is a breaking change if you do the opposite. So that's best handled by introducing a new name for the type of operation. Now the standard uses output iterators. I'm going to go for about 3 more minutes here and then we'll break and I'll take questions for the remainder of the time. The standard in C++ has the notion of output iterators, but output iterators tend to be complex and cumbersome. So they're isomorphic with the idea of a sync function object. Function objects are simpler to write with lambda expressions than trying to construct output iterators, even though we have adapters that can adapt a sync function into an output iterator. So operations like standard fill, iota, and generate would be better expressed with sync function forms. So ignore the wording on that slide. So for example, we could write iota like this and then call it like that, as opposed to having to call it with a, some adapter like a pushback iterator, or having to construct an entire iterator to do the operation that we want. So every algorithm using an output iterator, in my opinion, should have a corresponding form with a sync function. Algorithm semantics. You have to be careful, right, when you're using the standard library. The following code here attempts to remove the first odd element from a sequence. Right, the code's a little complex here. If we take a look at it, what are we going to do? We've got a vector A passing at 0, 1, 2, 3, 4, 5. We're using I'm sorry, I'd rewritten this slide, but apparently my slide deck didn't update. In C++ 20, you could use erase if, and so this would be simpler expressed with erase if. But here we're going to do the remove if followed by an erase. And what we're doing is we are passing a mutable lambda to remove if, which is going to return true for the odd elements. Okay. So what we're trying to do is remove 1, 3, and 5. If you see, it removed the 1 and the 3 in this case, actually, but not the 5. So what happened? Wrong. Well, inside, if we looked at the remove if, what we would find is that it starts with a find if, and it's passing the predicate by value. Okay. So now we've got 2 instances of the predicate. So we're going to skip, we're going to find the first instance that matches the predicate with 1 copy of our counter, of our odd checker, or yeah, of our counter, and then we're going to apply the remaining function with another copy of the predicate. So we could fix that by splitting out our item to remove the first odd iterator, and instead of making it a mutable lambda, binding to our counter by value or by reference. And so now we have the same code, and we're calling it to remove first is odd, and we call it, and it works. But does it fix the issue? Right? It doesn't. The requirement in the standard is that predicate is a regular, i.e. a pure function. Although the standard wording is a little obtuse, it goes like this. It says, given a GL value U of type, possibly const T, that designates the same object as star first, predicate U shall be a valid expression that is equal to predicate star first. All right. So what we're saying is that if we apply the predicate to a value, and we apply the predicate to dereferencing a position in the sequence to the value, that will give the same results. And our counter would violate that. There's no filter operation in the standard which guarantees the predicate is evaluated exactly some number of times or in order, right? So if you need such a function, you have to write it separately, and you have to have different set of requirements on it. So let's stop there, because the next section is going to be long. And open it up to questions, comments, input. Let's start with Robin. I see a hand up.
Hi, sorry, I joined late, somewhat late. Can I take a look at slide 43 or 44?
Sure. Let me see if I can slip there. (43) or 44.
Yeah. In the frame, the result of find is an iterator within the range from F to L non-inclusive. If the value is not found, the result will be range end, as I understand, which is outside of this range.
No, the result would be L, okay, because it's a half open range. So that would be,
and L is outside of this range.
Yeah, I get your point. Bad phrasing. So I think typically, yeah, with the standard when they're talking about positions, it's FL inclusive. So yeah, but I should probably draw that with square brackets.
Okay, thanks.
Yep. Thank you for the correction. Other questions? And they don't have to be about the talk if you guys want to ask about anything else. You got me here. AMA. Let's see. Jeff had his hand up first.
Yeah, just a couple of quick comments. I just noticed these things, but you've got a couple of slides that are either missing a word or there's one that's using the wrong form of there.
Ah,
So you might want to do a little bit of proofing before you.
yes, I definitely will. I was, of course, working on my slides here, and I did a bunch of proofing.
I just noticed these things, so sorry about that.
No problem. I was doing a bunch of work on the slides before this talk, and apparently my auto regeneration broke at some point, and I wasn't paying attention. I just assumed they were all getting auto regenerated. So a bunch of little fix-ups that I noticed through the talk were missing. I will do a careful proof of it. Let's see. I think Tyler had his hand up next.
Hi, thank you for taking my question. One of your points you made about code security intrigued me a little bit when you said that in order to, or at least I think you said, in order to make code secure, you had to make code correct. So I guess in your view, like what does make code correct?
Right. So that's, you know, necessary but not sufficient requirement for security. So I'm kind of a traditionalist, right? Right. What makes code correct? It's that you have a specification and the code matches the specification. The specification can include tests, and the code can be correct with respect to itself. So basically, correct code is code that's absent of contradictions, right? So if you have code which is crashing or triggering undefined behavior or things of that nature, that's code that's incorrect with respect to the C++ standard itself, which is a specification. And so is wrong, right?
And I get what you're saying. I guess in my mind, and please guide me here. There's like an unlimited amount of input you could ever give to a function or to a piece of code. So is it fair to say that it's never possible, or it's not possible to prove 100% correctness of code?
Oh, no. I mean, you don't have to test all the values. You have to prove, you know, logically go through and prove the code yourself. You know, there are a number of formal systems to assist with that. Lately, I've been writing almost all my code first in a language called Daphne, which comes out of Microsoft, and it can generate C code. I just hand use it to write the proof, and then I hand generate C++. But it does assisted proofs of code, and it's well integrated into VS Code. And so basically, if the compiler will compile the code in Daphne, then the code's correct, which is an interesting trait. Wouldn't scale well to a large system, but it's nice for writing small pieces.
I see. Thank you.
Yep. Let's see. I think Eric is there next. Eric, are you muted?
Eric is unmuted, but we cannot hear him.
Yes. Let's come back to Eric. We'll skip to Robert.
Hi, can you hear me?
Yep, I can hear you.
Okay, one of your very first examples had a function squirt I taking the square root of an integer, and then you had a precondition that x greater than equal to 0. But I got a little bit confused because that precondition wasn't enforced anywhere, not in the name of the function or in the code itself.
No, well, like I said, frequently, I mean, you could assert it in the code. I didn't have any code for squirt I just showed the interface to it. So you
Well,
could
what I
certainly
mean
have.
is, would it be better to just make it a square root of unsigned integer?
If you can constrain things to be by their type, yes, frequently you can't. But yes, I mean, you could do you could do that, and then require that your clients convert their integers into unsigned values before calling.
Right. I was just wondering though, the condition was just in the comment.
Yes.
And is that good or bad?
That is, in that particular case, I would probably assert it in the implementation. In general, though, you can't. For example, a lot of the standard library has the requirements that a passed-in comparison function is a strict weak order for all the values that could be compared. There's no way to write an assert is strict weak order, right? It's you would have to compare. Well, you could write it. It would just take longer than you have time for to compare all the possible permutations of all the values in all the different ways. So.
Okay, thanks.
So it's not practical.
Can you guys hear me now?
Yes, now we can hear you, Eric.
Oh, fantastic. Yay, Linux audio problems. So I've got like tons of questions for you about Val.
Okay.
You said it's a research language. Most research languages are never anything besides research languages. I sincerely hope that's not the case for Val. I think it's really interesting. I've been watching the GitHub repo. I've noticed I haven't seen any commits from Sean Parent come by. I'm wondering what your involvement in that is.
So my involvement to date has been, managing Dave on it. I did get a walkthrough because right now one of the efforts on it is building a transpiler. And so Lucian, who's one of the contributors on the project, gave me a walkthrough on the transpiler just a few days ago. And I'm hoping to make time in the next couple of weeks to kind of get my my feet wet in the code base, making some improvements to the transpiler. So that's that's where we are. So yes, you will probably see at some point a commit from me.
Oh, excellent.
So
by the way, you stole Lucian from me. Lucian was very interested in sender receiver and the P2300 executors proposal and was helping out with that. And then he discovered Val and got all excited. And now that's all he does.
Yes. So he's been a great contributor. So so I'm sorry, but too bad.
All right, I'll let somebody else.
Okay. Let's see. Well, Jeff and Robert have their hand up. They've both asked questions, but if you have a follow-on question, Jeff, go ahead. Nope, 2 hands went down. So any more questions?
Well, then I'll pester you with more questions about Val. Well,
okay.
I'm curious. Okay, like Adobe is funding this work. Where does Adobe see it going?
So for people who don't know, I'm kind of back to my ideal position here of managing software technology lab. which is a group I ran over a decade ago with Alex Stepanoff and Paul McJones and Matt Marcus and Foster Brereton, kind of the previous members. And now it's myself and Dave Abrahams, who is one of the creators of the Swift language and did the Swift standard library and the Swift UI work. David Senkel, who's from Bloomberg and is part of the C++ standards committee. And Nick DeMarco, who you probably haven't heard of, but he's somebody who I've worked with at Adobe in the past. And our charter is somewhat the same as the last time we had this group, which is to be forward-looking and improve the software that developers write in practice and not by process. Right, so we're looking at how do we improve the code that people actually write when they sit down at a keyboard, and taking a long-term view of that, not how do we improve it tomorrow, but how do we improve it 10 years from now. So that gives you some idea of where Val kind of slots in here, which is C++ has a lot of problems. It's a very unsafe language, and it's a very complex language. And those two things play against each other, which means it's just incredibly easy within C++ to make a mistake, which isn't caught by your compiler or even your sanitizers and your tooling, and takes your app down in a catastrophic way. And even if you stay within the safety guidelines, it's a complex language that's difficult to write correct code in. But Adobe has a massive investment in C++. So what's the alternatives? Maybe Rust. The Rust interop story with C++ isn't good at the moment, but it's getting better. There's a project, I'm trying to blank on the name of it right now, but there's a project to improve the interoperability of Rust with C++. There's Carbon, which is an attempt to address the C++ problems by fixing the governance of C++. I'm not yet convinced that that's a viable take, nor am I a particular fan of where Carbon is going. There's Herb Sutter's CPP2 effort, which is to embed a better language inside of C++. That has some more interest, I think, and follows on from the C++ guidelines. And in fact, we think that CPP2 is maybe not too far off from Val. And then there's our own effort, Val, which comes out of Swift. And so it is a language which is much more similar to Swift than it is to C++, but that has many of the attributes of Rust as far as safety goes. Kind of has, we say Val has all the safeties, but does so sitting on top of mutable value semantics instead of off of a borrow checker and reference semantics. And we just think the Val approach to the language is more approachable for your typical engineer than Rust is. Rust suffers a bit of the same problems that functional languages have, which means it's a difficult language to wrap your head around. It's not as bad as Haskell, but it's not too far off. So where does Val go? Unclear. Maybe Val becomes a successful language in its own right. We're a long ways from that. Like I said, we've got a start of a compiler, a start of a transpiler. It's not far enough along that we can even implement a standard library in it. We're hoping to ramp up here and get over that hurdle pretty quick. But a place to explore a set of ideas around kind of deep mutable value semantics within a language, and see how far we can push that, and see if we can take those ideas and inject them into the other efforts. Can we influence CPP2? Can we influence the C++ standard itself? Can we influence the Carbon project? Can we influence Rust? Can we influence how Rust integrates with C++? And I think already a lot of our thinking around Val has had an impact kind of on all of those fronts. So that's what I mean when I say it's a research language. We're not ruling it out as a commercially viable language, but I think if I pitched to the executives that our plan was that in 10 years we'd all be writing Val code, management would laugh at me because they understand what a Herculean effort that is around building up a tooling set that covers all the different platforms and environments that Adobe's code has to run in. Plus, it would have to be, successful enough that we could hire engineers that knew the language, and it's just a really long road. And even if we had the best compiler and a great implementation, it would still be a long shot to get there. But nevertheless, I think the effort has value, in exploring these ideas, and so that's our plan, is to push forward exploring these ideas, push forward with the compiler, push forward with the implementation, so we can play with these ideas, build out a standard library, understand what it would mean for this to interop with C++, and influence all the other efforts going on in the hope that one of them is successful, and maybe the successful one turns out to be Val. So that's our thinking. Hopefully that very long answer, but hopefully that explains like why Val.
Very much. Thank you. Thanks a lot.
Yep.
Best of luck. Yeah.
Thanks. Hey, Chris. We can't hear you, Chris.
Sorry about that. Got too many mute buttons.
Yes.
I just noticed P2676R0. Are you planning on trying merging Val into C++? Or object model? Or where's the direction of this? And I just discovered it, so I didn't get a chance to read the whole thing yet. But what is your goal with that?
What's the title of that paper? Because I don't know it by the number.
The Val object model, submitted by 4 guys.
Yeah.
3.
Right. So the Val object model paper was just because there was lots of conversations in the C++ standards community around safety and arguments about what safety meant, and things in Carbon where they're like looking at making everything pointers and getting rid of references, and just kind of directions that we thought were flawed. And so Dave took the time to write a short paper that just describes the Val object model to plant seeds and to get people thinking about it. There's no wording in there. There's no proposal for how that would integrate to C++. But if you look, like Sean Baxter's been borrowing ideas from both Val and Rust and putting them into his Circle compiler to play with them within the C++ space. And so I think we're having an effect. We're getting some awareness, and we're getting some people playing with the ideas and seeing where they could go.
Okay, thank you.
Yep. We're a bit over time, but I'll take one more question if anybody has one more. Going once, going twice. Okay, I think we'll call it. Thanks, everyone.
All right, thanks, folks, and thanks, Sean, for the presentation. Wonderful. As usual. If you can send me the slides, I'll get those posted as well. So. And now, Sean, we can't hear you.
I will send you a link. I will make sure that I get them updated and send you a link where to find them.
Okay.
Okay.
Thanks, folks, and we'll catch you next month.
Thank you.
Thank you,
See you
Sean.
next month.
Thank you.
Thank you.